Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. This is lecture number 67 and we will be talking about cryogenic temperature and doping analysis of tunneling current in ultra short channel nanosheet MOSFETs. So, we will be going into nanosheet MOSFETs and then in this lecture what we will be doing is trying to extract the current which is flowing through the device, both subthreshold current as well as post threshold current at cryogenic and with varying doping level. Okay, so let's introduce to you the outline of the talk. We'll introduce you to the talk and then have an analytical model and share with you some of the basic results and discussions related to this topic. If you remember when we were talking about nanosheet or double gate, let's see how a MOSFET structure looks like first of all. So, this is how a MOSFET structure initially looks like. What happens in a double gate is that if this is the metal and this is of course the source drain region here, which is N plus P N plus, this is substrate, right. So, what we do in a double gate is that we try to replicate the same thing at the back side of this. In a very layman language, I am using this term that you will have a channel here and then exactly the same as the top, right. And there will be two gates here which might be shorted. When they are shorted together, we define them as a join gate, and when they are not shorted with respect to each other, they are referred to as independent gates. So, there are two types of modifications. We do have an independent gate, double gate MOSFET, and we have dependent or a shorted MOSFET, a dependent gate MOSFET, double gate. Now, in both the cases, we apply a gate voltage here if the source is generally grounded, right. The source is generally grounded and we apply a drain voltage here, we apply a drain. This drain is also shorted, we apply a drain voltage here, because of which there is a current flow which is taking place here. Now, when we go for a nanosheet FET, we have already seen our previous discussion that they are basically sheets across which the currents will be flowing, and these are the basic sheets which are available. Larger the number of sheets, more will be the current carrying capability of the device, right. So, this we have already learned from our previous discussion. Of course, a nanosheet MOSFET, it's nanosheet MOSFET nonetheless, and we will have a better control over the channel, right. And as a result, your short channel effects will be drastically reduced in case of a nanosheet FET as compared to a double gate MOSFET even. So, with this basic knowledge about the structure of the device, let us introduce to you the basic formalism which is there. And the idea here is that as you go on modifying the structure of the device and try to shorten the width of the device. So, let us say I have this dimension is, let us say, approximately say 2 to 3 nanometers, right. Then there is a quantum confinement effects comes into picture, right. And when the dimensions becomes of the order of wave function of the electron, you need to take the quantum mechanical effect. So, the idea here is that when lambda, which is given as h cat by mv, right, for an electron, when this becomes of the order of the dimension of the device, then we are in a sense more physically plausible answers will come when you take quantum confinement or quantum mechanical models available to you. So, I am assuming that I am going into the ultra short channel regime, and as a result the dimensions are extremely small in nature, because of which there will be quantum confinement. Now, therefore, when the quantum confinement comes into picture, we need to solve the Schrodinger and the Poisson equation in a self-consistent manner, right. Now, typically there are multiple ways of modeling a nanosheet FET or a double gate MOSFET for obtaining the current. One of them is basically a non-equilibrium green functions formalism, which is referred to as NEGF, right. And in this paper which I am referring to is implemented on a nanomos. Nanomos is a tool in which they use non-equilibrium green function comparison. Now, over a period of time, device modeling people have used self-consistent solutions of quantum confinement and Schrodinger equation. The Schrodinger equation can again be two types, time independent and time dependent. and depending on whether it is time independent or time dependent, you can do a transient analysis or a DC analysis. Now, what does quantum confinement do is that rather than assuming that the electrons can flow in energy scale across the whole energy scale in all the energy scales, quantum confinement restricts them to move in a certain energy subbands, right? In a very strict in a sense, energy subbands are there, and these are very ultra thin channels. Thin channels are formed, and these ultra thin channels are energy domain are very thin in nature, and they allow the electron to move from source to drain in a much better manner. While you introduce these quantum mechanical effects, it does what? It actually reduces the intrinsic carrier concentration, effective intrinsic carrier concentration, and also increases the threshold voltage because of band gap widening, right? Now, it has been seen the second order effect, for example, DIBL or SS, subthreshold swing. Subthreshold swing is not a second order effect, DIBL is a second order effect. The quantum confinement does not influence drastically the double DIBL or SS, right? What is SS? SS basically is the meaning of subthreshold swing, which effectively means that the change in the voltage on the gate side, so that you have a 1 decade change in the output current. And what is drain induced barrier lowering is when you bring the drain and source closer to each other because of the change in the drain potential, there will be lowering of the barrier on the source side, because of which there will be a tunneling happening on the source side, and there will be change in the threshold voltage because of that. Now, what we are assuming for all these discussions is that there are no thermionic emissions, and only basic thermionic emissions are considered, and they are all valid for short channel transistors. So, two things which we are considering here is that we are assuming that we have a short channel we have, and the short channel is basically assuming that there are no scattering or traps available to us, and therefore there is no thermionic emission. Whatever is there is because of basic nature of the device itself. We are also not considering too much amount of change in the SS or dibble, and we are looking into direct drain to source tunneling. So, that is referred to as DSDT, right? That is DSDT here, right? And then you have thermionic emissions which are considered here. Now, typically, what do you mean by self-consistent solution of Schrodinger and Poisson is that you extract the wave function from the Schrodinger, and from their wave function you try to extract the probability of finding electron within the system. And then from there you try to extract the value of the surface potential, and from the surface potential value try to solve the Poisson equation to get the charge, right? From charge you can actually get the value of current and how the current varies with respect to drain voltage and gate voltage. So, the schematic of a double gate nanosheet field effect transistor is shown on the right hand side here at this particular point. This is my N plus gate here, right, and this is my N plus drain. So, I have fused the top and bottom gate, top and bottom one. This is my source potential or source contact, this is my drain contact, and these are the gate contacts available. LSD is the source region length, and LS in this drain length is this thing DD. This should be LDD, a drain dimension. Now, this is the source drain extension region which we refer to in many cases, and this is a self-aligned structure where the metal layer is almost aligned with respect to the intrinsic nature of the silicon. So, if you reduce the dimension of the device, then you also not only reduce in the longitudinal direction, you also reduce in the lateral direction. So, this direction also gets reduced drastically. When this gets reduced literally down to a low value, then you will always have a confinement, as I discussed with you in the earlier case. Now, the channel is basically an intrinsic channel, very low doping. By Dennard scaling law, if you look, they will be very effectively a very low doping will be there. And this low doping region is sandwiched between the two oxide and the metal layer at the top and the bottom, right? And there is an oxide layer here, and then you have the black color is basically the metal gate. So, this is your M, this is O, and this is S on this side, this is M on this side, O, and this is S on the other side. Source drain region are very heavily doped. So, I have an N plus P N plus junction available to me, right. So, I have a junction which is N plus P N plus junction, right. and therefore even if you don't apply any bias on the source or drain side, there will be always a depletion region will be more extended towards the intrinsic region from both the sides. So, the effective channel length will be reduced drastically. Gate electrodes are always at the top and bottom, and therefore now the channel is surrounded on the two sides, and therefore a relatively a better control as compared to a bulk MOSFET. The channel length is referred to as LCH, and the channel thickness is TCH, oxide thickness is TOX, and the source drain extension region on both source and drain side is referred to as LSD. So, this is considered as X direction, this one, and this one is considered as Y direction. So, the current is flowing on the X direction and the control is via the Y direction, right. The flow of the charge carrier is because of the application of drain potential on the drain side, and because of which there is a charge carrier which is moving from this way. Now, if you look at the conduction band profile between the source, channel and the drain for a double gate device, and this shows the conduction band edge on this yellow colored one, if you see very clearly, it's a conduction band level is there. The yellow curve represents the conduction band profile, right, and as you can see here, if you apply a bias, since you have applied a bias here which is of VDS equals to 1 volt, the conduction band profile on the drain side is actually dipped well below because it is minus Q into V energy scale, and therefore when you apply a voltage of plus 1 volt minus 1 into, so it's basically minus Q into V. So, when you apply a voltage of 1 volt here, and that's the reason it is dipping down from its nominal value to a large lower value, right. Whereas, on the source side, since you have given 0 bias, you typically don't have too much amount of change here. However, on the gate side also you haven't given any bias, and the gate side you will see a hiring of the potential on the source end. And if you look very carefully, this is not perfectly symmetrical. This height going very high is not perfectly symmetrical. It is more shifted towards the source region here, right. It is more shifted towards the source region, and this is because you are giving a potential on the drain side, forcing it to lower, and therefore that shifts the peak of the conduction band edge more towards the source side, right, and that's what is shown here. The this is basically my electron energy distribution, right. This is the electron energy, this one, and this one is the electron energy distribution which you see. Now, a barrier is formed in the channel region, and the electrons actually tunnel through. So, let me just rub this portion. So, if you look here, I have a barrier here, and the electrons are basically tunneling through this barrier and reaching the other end, and this is known as DSDT, which I discussed in the previous slide. This is referred to as DSDT, that because of a rising potential, the channel tunneling will take place through the region, and we are using a channel length of 6 nanometers, and we are taking thickness of 2 nanometers. So, if your thickness is so small that the quantum confinement effect comes into picture, right. So, I have taken VDS equals to 1 volt and VGS equals to 0 volt. So, when I see 0 volt, no bending of the band takes place, but when I apply a 1 volt, it shifts downwards to a larger extent, and that gives you a conduction band profile here. Now, let us take up wavelet approach, which is basically an approach which is basically more accurate as compared to a WKB approximation model, especially for low energy electrons. Now, WKB approximation inherently assumes that your perturbations are very low, right. WKB approximations assumes that your WKB assumes that your perturbations are very low, right, or second order perturbations are low enough, right. But that is not the case always, right. There will be always a perturbation which will be available. So, I want to find the turning probability through this region using a wave function distance. Then if you do all sorts of mathematics, this comes out to be equals to this thing, where we define the tunneling current density J of t, which is a function of y, is equals to q times m effective mass of the electron divided by 2 pi square h cut cube integral 0 to em, right. Em is the maximum energy which you see there, p t y e x, right, times n e x dx. What is PT is the tunneling probability at energy Ex, right. So, at energy Ex, what is the tunneling probability? is always space dependent and energy dependent, and therefore I write Pt as a function of y and Ex, and n of Ex is the supply function included in that. So, this is basically coming from FD statistics, Fermi-Dirac statistics, which is coming FD statistics, right. M effective we are assuming to be equals to 0.19 effective mass of electrons. So, what we are assuming is that when there is a barrier available, then the effective mass of an electron becomes equals to 19% of the actual mass of the rest mass of the electron, right. And we are integrating it from 0 to Em. Em is basically the maximum energy to which the barrier is located, right. Ex is basically the energy at any point x in the channel, and Pt is the tunneling probability. And h cut you are already aware of what these values are. So, it means that higher the value of M effective or higher is the value of effective mass, the tunneling probability will actually show an increase, right. And similarly, if your Pt y of y and Ex are large, you will also see a large amount of tunneling probability, right. And why this is a probabilistic phenomena? Because the tunneling is via an intermediate state of energy through the tunneling barrier. Ideally, if you look at the classical barrier, the electron will never be able to cross through, because the potential energy of electron is smaller than the barrier potential. But if two energy states are very close to each other in this region, right, and in this region, then there is a finite probability that they will match with each other and there will be a substantial amount of tunneling taking place, right. And that is the reason we refer to this as the channeling probability in this case. Now, n of Ex, which is basically the Fermi function, is given by this. You might not be able to understand looking at this, but let me write it down for you. Q into thermal energy, natural log 1 plus exponential minus of Ex minus Efs, right, divided by Q times Vth, and then this whole thing is basically divided by 1 plus exponential minus Ex minus Efd. I will explain each one of them individually and explain to you, right, divided by Q times Vth. This is where n of Ex. Now, looks complicated, but it is not. Ex is basically the energy at any point x in the channel, and Efs is the Fermi level at source, Efd is the Fermi level in the drain, and Vth is the thermal equivalent voltage which you get. And from here we can see that, let us assume that if I assume that, let us say E equals to Ex equals to Efs, right, then this becomes almost equals to 0, right. So, it will becomes e to the power minus 0, right, and e to the power minus 0, this whole thing will become 1, 1 plus 1 is 2, natural log of 2 will come out, right. So, it will be Q Vth natural log of 2 divided by some value, which means that if Ex becomes equals to Ef, then the probability function actually increases drastically, right. Now, total current density is given by the tunneling current and the thermionic emission current density. So, J of Ty is the tunneling current density, and J of Tey, this is the tunneling current density, right. This is the tunneling current density, and this is my thermionic emission current density. Now, both are to a larger extent temperature dependent, right. So, that is the reason cryogenic is coming into picture in both the cases. Now, the total drain current which we get is nothing but the total current which is given here, this one JDS, right, that we take up and we place it here and we multiply with dy, because y is, if you remember, y is the longitude, this direction, the y is this direction, right. So, we need to confine the channel in the y direction, therefore, we multiply with dy, because both Jt of y and Jt of y are basically the current density in the transverse direction. You multiply this with dy, and then you multiply the whole thing by Wch. Wch is basically the width of the channel. So, you are basically integrating in the with direction, and you are integrating from minus TCH by 2 to plus TCH by 2. So, IDS is basically given as minus, actually W TCH by 2, 2 plus TCH by 2, J JT, sorry, JTY plus JTEY into dy into WCH, right, and that gives you the value of IDS, and WCH is the width of the channel. So, you are basically integrating across the width of the channel, and what we do is that we try to extract the conduction band profile in the Fermi level directly from NEGF, from non-equilibrium Green functions formalism, and this is to avoid basically the misfit in our design. Subthreshold swing, we have already discussed what is it. At low temperature are actually explained by NEX function. NEX function is which function? This function, and the subthreshold swing is defined by this function to a larger extent, and this is referred to as the supply function. And basically the supply function describes the number of electrons which are available for tunneling on thermonic or thermonic emission at a given, because with at a given energy Ex. Now, if a given energy Ex is there and that is more than the band gap of the material, you will have large amount of electrons and hole pair transitions taking place, right. These transitions are such that there will be jumping of electron from the conduction band up to the from valence band up to the conduction band, and as a result you will have relatively a larger number of electrons available for tunneling. Now, what we do is, not if we analyze the cryogenic effects, then we try to find out the ratio of NT to N of 300 Kelvin. NT is basically the number of charge carriers at temperature T, and basically the supply function, and we try to find out the value divided by number of the transfer or the supply function at 300 Kelvin. This is the room temperature. So, once you find the ratio, so at room temperature this factor will be equals to 1, and cryogenic we will see how it varies over a period of time. Now, this figure on the right hand side shows the variation of N of T with respect to N of 300 with respect to temperature. As I discussed with you, at 300 Kelvin you will always see all of them are merging to 1 here, all of them are merging to 1, and that is expected also because N of T is basically N of 300 at 300 Kelvin, and therefore they will merge with each other. And the blue curve is basically the case when Ex is less than the Fermi potential at source, and this is one extreme, and basically the other extreme is this one where Ex is equals to is much larger than EFS. So, one case is when Ex, the energy of the electron is much smaller than the Fermi level at the source side, and then another edge of the probability is much larger away. Now, as you can see here, the when Ex is much less than Ef of S, right, their availability remains constant across the temperature, and that is what is written. This is a flat curve. If you look at the blue curve is almost a flat curve, implying that N of T by N of 300 still remains 1 at very low temperature, and it does not change provided the value of the energy is much smaller as compared to the Fermi level energy of the source side. For energies below EFS, right, if you are fixing the energies below EF. So, what is happening for energy below EFS? The electrons availability is almost temperature independent, and that is the reason why subthreshold current does not vanish completely at low T. Why? Because even at low T you have still low temperature, you still have some charge carriers which can participate in the switching process, right. Now, when E equals to EFS, let me just check right, when E equals to EFS, the second curve, this one, electron are at the Fermi level and the supply decreases so slowly as the temperature goes on increasing. So, if you look very carefully up till 50 Kelvin here, right, this function is almost a straight line, almost very small decrement in the function, but below 50 it shows a very steep fall, and that is primarily because of incomplete ionization which you get in this case, right. Now, if E is greater than EFS, which is the third case, this one, black one, the electrons are slightly above, I am saying that the Fermi level, the Ex energy is greater than Fermi level, which means that there are certain states available to you which can participate in the charge carrier distribution. their availability decreases significantly at low temperature, even at 150 and down below 200, and at 50 very very low value, 10 to the power 5, -5, -6 values. Now, for energies below EFS, which is the Fermi potential at the source, electron supply decreases rapidly with decreasing T, and this causes the subthreshold swing to saturate instead of improving indefinitely. So, the subthreshold swing actually saturates very fast, right. When Ex is much larger than Ef of S, right, which is the last case, the supply becomes almost negligible as temperature decreases, right. And therefore, the relative immunity of the subthreshold current to the variation in temperature lies below Ex. So, the most variation in the subthreshold current you will see is when your Ex is much larger than the Fermi potential, which means that if a large fraction of electron comes from Ex greater than Efx, then lowering T strongly reduces the current, and this is the thermal component of thermionic emission. And this is where the thermionic emission restricts the number of charge carriers in the device itself, in a double gate device. So, I think we will stop here for this lecture, and I hope you enjoyed it. Let me recapitulate what we did. We actually studied a double gate MOSFET. We understood its modeling technique. We understood what is the meaning of Fermi levels and tunneling. So, there are two tunnelings which we are considering. One is thermionic based current, another is a tunneling based current. We add them two together to find the total current. And finally, which we are discussing now is that if the energy of the charge carriers are above or below the Fermi level at the source, how does the fraction of electron contributing to the total current change as we move from a higher temperature to lower temperature. Hope you enjoyed the lecture. Till we meet next time, bye for now.